Okay. Okay. Now you are. Right? So, length, displacement, and then we also got it is mass, and also what else? Time. Okay. All right. And then number 4 is temperature. Number 5 we got it is light intensity. Okay. And then number 6, number 7, what else? Right. Number 6, I think. So we got it is more subtle, okay, and so on lah. Right. But normally, in the real application, we most of the application requires you to measure some displacement and some mass. Yep. And temperature. Yep. This is most of the variable that you will play around when you want to do some measurement, right? By using the instrumentation. Okay. In these lectures, what we're going to look at is the performance characteristic for measurement and instrumentation. Measurement is about when you get the data. Okay, so what you will do with your data. Instrumentation is about a transducer and also signal conditioning and so on. There are 4 components there. And the performance characteristic, so the word is performance, okay, and then characteristic. All right, so this one we going to look at. Okay, when you want to decide, okay, for example, you want to measure the temperature, so you need to know what your uh, what we call it requirement that you want to measure. Is it you want to measure the temperature starting from 0 degree to 1000 degree? Okay, so maybe you work at oil and gas industry, so they requires this, right? So and then you start to searching what is the type of transducer, especially the temperature transducer that you're going to choose or to use. Okay, and then you will look at the data sheet or manual and so on. Okay, and then when you look at the data sheet, right, there are certain unit that you will found it. For example, you found the word accuracy. Okay, and then you will found the symbol plus minus. For example, this one 0.28 degree. Okay, and then some of you will found the words is the accuracy, plus minus, it's not plus minus, this is 0.25% full scale. So this is what, okay, and then you found that some of the data sheet show that the range, okay, the range 0.5 to 5.8 psi. Okay, and it shows that yep, it can go to range 40 kPa, and then what is the electric current and so on. So this is what you get it from the data sheet of the transducer or sensor that you going to use. Okay, all right. So uh, when we talk about performance, we can divide it into three categories. Three categories. First is the operational characteristic. Okay, and then second is static characteristic, and the third one is dynamic characteristic. Operational characteristic, this is the first thing when you want to buy the transducer or sensor, you will look into that. Okay, it is include what is the range of the transducer can support, what is the span. Okay, this span, all right. Some of the data sheet they use the word span. Okay, so how to get the span? So you can go to the any shop and then you can buy span, right? Right. Ha 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 ha. Okay. If the WeBack meeting can have the ha ha ha, is quite nice, right? So if not, I just will talk by myself, right? Okay. And then is also include what is the anything anything else that you going to look at when you want to buy the sensor. And then the second part, we look at the static characteristic. What is it? We will discuss later. And then dynamic characteristic. So it is enough if you have know about these three things. Okay. Right. So let's look the first one. Operational characteristic. That's mean that transducer it will operate. So that's mean it can meet your requirement or not, depending on the data sheet. Okay, so range, the word range, that's mean minimum to maximum. So you can see that, yep, if you want to buy the pressure sensor, it show you the range. Okay, now you can get it. Oh, the range is 0 to 5.8 psi. Okay, or if you write a 0 to 40 kPa. All right. Okay, this one. So if you want to measure the pressure is inside that range, so yeah, you can consider this transducer. Okay, you can consider this type of transducer. All right, and then the span, only the difference between maximum and minimum. Okay, uh, span is only some of the manual or data sheet you show yet. You don't write range, you just write span. Okay, span equal to what, right? So that's it. And then sensitivity. Yeah, sensitivity is that's mean the ratio between output and input. Okay. Some time we call it is a transfer function. Okay, transfer function TF. So what is mean? For example, you want to measure the quantity is temperature, and then the output when you look at the sensor that you're going to buy is give you the output millivolt. So what is the sensitivity? Sensitivity is the output over input. That's mean millivolt over degree. Okay, so this is the first concept that you need to understand. All right, and then for example, when you look at on your data sheet, okay, it give you the sensitivity is equal to 2 millivolt per degree. And of course, if you got it, the temperature you measured is 100 degree, then you can get the output, you should get the output is 200 millivolt. Okay, right, this is the concept lah. So by looking at the sensitivity, so we can know that the output that can we get it. All right, for example, the galvanometer here, it shows that the temperature is 17 millimeter per microamp. All right, that's mean if you draw the block diagram, and it will look like this. Okay, this one is millimeter over with microamp. Okay, so which one is the output, millimeter or microamp, guys? Ah, millimeter. Yeah, 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 yeah. Francisca Pawi, are you from local or Indonesia or from Francis? Sorry, I can't hear you. Malaysia or Francisca Pawi? Oh, sorry. Okay. Right. Uh, guys, is it clear? My voice to you?
Yes, very clear.
Okay, thank you, Yan. Yan. Oh, Yan. Oh, let's call you Yan, right? Yan Zingji. Okay.
Yeah, correct.
Uh, all right. Uh, where am I? Okay, I'm at home. Okay, good. All right. So when you define the sensitivity, you can look at, yep, the output is milliamp, the input is microamp. That's mean if your let's choose another color. I don't know. Sometimes I'm not good in choosing any color. Okay, if your input is 1, right, 1 microamp, then the output, yep, before that the sensitivity is show that 70. So the output will be 17 mm. Okay, that's mean your scale, right? Your scale or the pointer of the galvanometer, it will move to 17 mm. Okay, all right. So that is the sensitivity under the operational characteristic. All right. And then the other parameter is right resolution. Okay, resolution. Of course, if you buy with a good resolution, right, you can see that your instrumentation or transducer will give you very accurate value. Okay, a good resolution. For example, right now before this we only have the HD. Now we have the 4K, and then after 4K we have the 6K. Right. So HD, yep. What is mean HD? Yep, I can show it to you. Maybe for the HD, right? So 100. How much is it? 120. Uh, I forgot about it. Okay. So let's say for HD 100 times 100, right? So that's mean for this pixel, you can get it. One time one, okay, one time one, okay, and then for maybe for 4K, right, so 1000, okay, and 1000, right, so you can get it very small, it is very small, right, so yep, pixel very small, and then that means your uh uh pictures, right, it will be very sharp. Okay, okay, this is the example that resolution. Okay, how about the transducer? Let me give some example here. Okay. For this sensor, pressure sensor, right? Okay. It's only give you the range 0 to 5.8 psi or 0 to 40 kPa, right? And then it give you the accuracy 0.25% time with full scale. Okay. All right. So, and then it don't show the word resolution, right? So, for example, maybe your measurement that you going to measure, all right? Maybe it will take about let's say the kPa. Okay, the uh, smallest value that you going to measure maybe is 10 kPa. Okay, maybe, alright, is very small, right? You want to get a transducer that can detect at least 10 kPa, alright? But according to this datasheet, you only got a range 0 to 40 kPa, and then the accuracy 0.25% time full scale. So where is the resolution? Where is the resolution? Guys, where can you get the resolution? Is it from the range or is it from the accuracy? How about you guys? Ki Hui Fung, yes. Where you can get the resolution? Is it from the range or from the accuracy? Huh? No answer?
You know,
Oh, you are girls. I thought that you're boys. Okay. All right. Nice to meet you. Okay. You can get it from the uh yeah, okay. You can get it from the accuracy. Okay, this one 0.25%. You time with full scale, that's mean the maximum the transistor can be measured it is 40 kPa. Okay, let's choose the 40 kPa. Right, let's choose the unit kPa, right? 0.25 you time with 40 divide with 100. Okay, that's mean you can get it 0.1 kPa. Alright. Okay, so it shows that this transducer, it the smallest unit that it can measure is 0.1. Okay, kPa. So is it enough for you to measure the 10 kPa? Enough or not? Enough, right? Okay, the smallest that it can measure is 0.1. Okay, you you want to measure 10, right? So it can measure until 0.1. Wow, is enough. You can use this one. And also the range, it can go up to 40 kPa. That's mean it depending what's the maximum value that you're going to measure. Okay, the solution and also the threshold. Threshold, that's mean the largest value or that you cannot measure. For example, for this case, the 40 kPa is the largest value. So that's mean if you want to measure the pressure at 100 kPa, that means you cannot use this kind of transducer. Okay, guys, so far so clear. So far so clear. Is it? So far so clear? Okay. Okay. Yep, this one. This one. Oh, this one and Aizat kan? This one. Awak kah? Ah, okay, okay. Aizat ada. Okay.
Ada.
Aizat ada. Okay. Aizat dalam kereta ke apa?
Tak nak kat rumah.
Kat rumah. Apa tak balik UTM ke?
Tak.
Tak. Alah, selesa dekat rumah.
Ha.
Dari segi makan tu kena jaga ya. Rizwan Yaakob pun dulu saya jumpa dia kurus saja. Ini tak tahulah ni, tak nampak gambar. Boleh tunjuk gambar ke? Ataupun dah berkahwin? Belum?
Belum.
Okey, yang lain tu I don't know lah siapa yang saya kenal-kenal ni saya tak apa kenal. Sorry guys. Okay. Alright. This is the operational characteristic. Okay. And then the second one is static characteristic. Okay, static characteristic, there are two parameter in this, which is the error and then is the accuracy. Okay. Alright. So error, yep, you can it's only the difference between the actual and the measured. Okay, that's why you got an error lah. Okay, and then the gross error, blah blah blah, is the we call the human fault. Systematic, it is cause of the equipment or device itself. Okay, of faulty of the instrument. Okay. And then accuracy, so sometimes we try we just assume that accuracy and error give you the same meaning, right? Okay, and actually the accuracy that's mean is it give you some uh, common sentence. Okay, that's the accuracy, and then actually from the accuracy you can get the error. Okay. Right. You look at on this data sheet again. Okay. If you look at, yeah, in this sensor, it gives you the accuracy here. Accuracy is equal to plus minus 0.28 degree. Okay. But this one, it gives you the accuracy 0.25% time to scale. Okay. That's why sometimes when you look at the datasheet, different manufacturers they will write different different, what we call it, different standard or different words lah. They will use the different word. Actually, it will give you the same meaning lah. Okay, alright. If you see that in that data sheet, it shows that, yep, accuracy is plus minus 0.2 degree, for example. So this one, it gives you the accuracy equal to plus minus 0.2 degree. So in order to find the error, error is equal to plus minus 0.2 degree. So you can straight away use the value from the accuracy is become an error. Okay, so this is the example. And some of the data sheet, all right, it shows that the accuracy, for example, this one, plus minus 1% full scale. Okay, this you need to convert it first, accuracy plus minus 1% full scale. Okay, then you need to find the error first. So error, that's mean plus minus 1 over 100, which is 1%. You time with the full scale. Full scale is the maximum value the sensor or instrument that can detect. For example, like this, it shows that the full scale is 10 m, then you will get the error, uh, which is equal to, how much is it? 0.1. Okay, 0.1 m, right? So that's it. Okay, sorry, is have the plus minus. Okay, so it gives you some general idea lah if you look at the difference, if you look at in the data sheet of the transducer that you're going to buy. Okay, and some of the manufacturers is shows that plus minus 3% span. Okay, so how to get the span? So you can go to the shop and then order, give me one span. Okay, no, you just from the maximum you minus with the minimum. Okay, and then some of the datasheet, it doesn't give you any words after that, plus minus 2% only. It doesn't give you the push scale, span, and so on. So this one, what you need to do in order to find the error of from the accuracy, you need to tie with the uh, reading, the true value that you got it. Okay, for example, the true value you got it is 2, then you need to time with plus minus 2 over 100, then you will got it, the error 0.04. Okay, in this case lah. Alright. Okay, so what can we conclude that uh, all the manufacturer, they don't use this one standard, right? So some of them love to use like accuracy plus equal to plus minus 1% per scale. Okay, some of them just use plus minus percent span and so on. Okay, all right. Then the most important thing is you need to convert into the error, because when we get the data, then we will put it, yes, this is our data, but the actual value, you need to plus minus with the error. Okay, all right. That is the static characteristic. There are two things, error and accuracy. So from the accuracy, you can get the error. Okay, all right. So far so good. Any question? Ada apa soalan, guys? Yuhu, guys.
So far, no
Ada?
questions.
Yan. Hey, so cute your voice. Okay, good. So far so good. Right. Have you eaten? Have you took your breakfast, Yan?
Yes, just finished it.
Okay, where are you right now?
At home.
At home also. Okay, good. Everybody at home, right? Okay. Never mind. Just for your information, so for your exam, mostly maybe will be face to face lah, maybe lah. But that one is still in discussion, right? They will do like SPM, right? So if you your home is far away from UTM, so maybe you need to go to at one hall or day one there, then you will sit there to to take the exam, right? So but that one is still in discussion lah. Okay, it it will be good, right? It will be good for you. Uh, uh, yeah, good for you. It's not accused for the TS, right? TS issue. Hmm. but you can imagine that yeah, how much the UTM we spend for the pengawas. So what we call it, pengawas. Okay, to be there in each hall. I don't know. Okay. Any question you can interrupt me. Okay. So if not, I will short sendiri lah. Okay. I don't want to be short sendiri. So I want to understand what your understanding about my lectures. Okay. Example 3.1. This one is very simple example lah. Okay. A temperature sensor has a range 20 degree to 250 degree. The measurement result in a value of 55 degree for temperature. Specific that the error in the accuracy is 0.5% full scale or 0.75% of span and so on lah. Okay. So you can proceed this one. This one you got the temperature is 55 degree. Accuracy it give you 0.5% full scale. That's mean from this one you can get the error 0.5 divide with 100 you time with the full scale. Yep, full scale that's mean is the this one the maximum transducer it can measure. That's mean is 250 degree. Then you will got it is plus minus 1.25 degree. Okay, and then the possible temperature that's mean if you measured 55 degree then you will got it is plus minus 1 to 5 degree, right? So that's mean your actual temperature it should be around 56.25 degree and then 53.75 degree. Okay. Guys, you want to copy first or what?
Kopi dulu lah.
Oh, copy dulu, okay. Uh, copy and paste, copy and don't forget to distribute to your WhatsApp group, okay. During the test and also exam, okay. Alright, done. Okay, so I think this one is simple lah, simple. So 0.75% of span, you can find the span 250 minus with 20, maximum minus with the minimum. Then you got it is 230 degree. Okay. Then the error plus minus 0.7 over 100. The time of span is 230 degree. Then you got it is around plus minus 1.7 to 5 degree. Okay, and then your temperature is 55 degree plus minus 1.7 to 5 degree. Okay, right, this is the answer lah. Then for the reading, then 0.5 or 0.8. The reading that you measured just now is 55 degree. Then you got it is plus minus 0.44 degree. Then your actual reading will be plus minus 0.44 degree. Yes, so done. Okay. Example 3.1 is simple. So you just understand the concept. From the accuracy, you need to find the error. Okay, done, guys. Boleh? Done, Okay. I hope you done. Okay. Dah copy, Dah copy kot. Senang lah. Tak ada masalah. I hope that you got it. The student note, student note. It's not the lecturer's note. Okay. If if not, you don't learn. Not. You will learn nothing lah if you got it the lecturer's note. I know you can get it right from your senior or maybe from the last semester and so on. Okay, example 3.2, a temperature sensor has a transfer function 5 millivolt per degree. Okay, he got it, the transfer function 5 millivolt per degree. Okay, that's mean the output is millivolt and then the input is degree. So this transfer function have the accuracy plus minus 1%. Okay, so you got it is 1% here. And find the possible range of the transfer function. Okay, all right. So it asks you in this question, what is the possible range? That means the transfer function is millivolt per degree, and then it have the transfer function 5 millivolt per degree, and then it asks you what is this value? Okay. That's mean the error lah, plus minus something the error. So that is the question is about. Right? Okay, so we can find the error first. So plus minus 1%, 1 divided with 100. You time with the transfer function 5 millivolt per degree. Then you got it is 0 plus minus 0.05 millivolt per degree. Okay, alright. So the possible transfer function is 5 plus 0.05 millivolt per degree. Okay, right. So that's mean yang this one. Okay, then here we got it. Boleh padam ni, dahsyat ni. Plus minus 0.05 millivolt per degree. Okay. Last semester I'm using the whiteboard. Okay, so I put the sound camera and using the whiteboard, and it's like you are in the real class. Okay, but and then I just upgrade from the whiteboard to the iPad, right? I'm using the Apple right now. Okay, okay, wah. Yeah, in the online class lecturer we try to laugh by himself, right? Ha 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 ha. Guys, come on. You need to laugh also. Ha 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 ha. Okay. Any questions so far? Oh, you can put it the okay. Oh, how to do that? Oh, we got a reaction. Okay. Oh wow. Oh. Thanks guys for your cooperation. Okay. Let's move. Example 3.3. Okay. Now you got the possible transfer function from here. Okay. You got it from the previous example, and then it give you some example, some situation. You got a reading is 27.5 millivolt. So what is this temperature? Okay, so it's quite simple lah. This one is X. You time with this transfer function, then you got it this one. Okay, so like this one, X. You time with this one, then you got this one, then you can find X lah. Okay, right. Find X. Where is X? Here. This is X. Find X here. Good. Okay. That is quite simple. Example 3.3. Okay. The previous example that have shown before is more about on transducer itself. So when you have the instrumentation system, remember the instrumentation system have four components: transducer, signal conditioning, analog to digital, and also display. Okay. Most likely, maybe your system will require two signal conditioning. For example, you will have the transistor signal conditioning and signal conditioning. Signal conditioning 1, signal conditioning 2. Okay, and then from that one we can determine the accuracy, okay, of the overall system. Okay, so for example, your transistor it detect a degree, right, which is dynamic variable. Yet, of course, the temperature will change over time, and then your output of your instrumentation will be in terms of voltage. So you detect the degree, and then you get the voltage. Okay, and then your instrumentation has the transistor and also signal conditioning. Okay, so how to get the overall accuracy? So we need to do some calculation a little bit here. Okay, all right. So let's start this one. Now you have here. That's the okay, the output V plus minus delta V. Okay, plus delta V is mean the accuracy. Okay, this mean the accuracy. Alright, this mean the voltage lah. Okay, the value. Okay, I put it this the value. Okay, or data. Alright, or measured data. Okay, that's it. So C you time with K time 1, K time all these things you get it K plus K delta K. Sorry. So this one you only got it delta K. Is it? Okay. And then this one time this one, you time this one, you will got it is G plus minus delta G. Okay. Okay. So you got it this one, delta V. Okay. Then we can group for the output voltage and error accuracy. Okay, so we got it is V equal to C kg, and then we can get the error or accuracy equal to C plus minus. Okay, now we got this one. Then in terms of fractional uncertainty, okay, accuracy sometimes we call it is uncertain. Okay, uncertain. Okay, we don't know uncertainty. Okay, that's it. Right. So for error for output, okay, error is your error is for output, error and accuracy, okay, is equal to oh it's not enough. G top this doesn't have this one. Okay, delete. Oh, okay. C delta K delta G over with a V is C K G. Okay. Then you will found that you will cancel each other. This one you will got it plus minus delta G over G plus minus delta K over K. Okay, delta V over V. Alright. Then you got it is plus minus uh, delta k delta g over vkg. Okay. And then the overall accuracy uh, is only delta k over k plus minus delta g over g, and then we can ignore this one, right? We can ignore. Okay, why? Because delta k and delta g will give you a very small value. Okay, for example, if you got a delta k around 0.01, you time with delta g 0.001, then it will give you very small value, and then you divide with k and g where is a very big value, for example 10, you time with 200. Okay, so it is almost zero. Then you can ignore lah. Okay, right. Guys, done? Sudah habis kopi? Belum lagi. Belum lagi ya. Okay. Done, guys? Okay, can I move to the next slide?
Yes.
Okay, good. Can you give thumb up? And thumb up. It's not thumbs up, thumb up. Okay, thank you guys. All right. In terms of the percentage, yep, you just time it with the 100%. Okay, and for the root mean squared, yeah, this is the formula lah. Okay, okay. Let's do the example for the overall instrumentation system in terms of system accuracy. Okay, find the system accuracy of the flow process in the transducer transfer function. It gives you 10 millivolt per QQ and so on, plus minus 1.5%, and then a signal conditioning system transfer function and plus minus 0.5%. Okay, if you look at this one, when you play around with the transfer function, this one that's mean delta k over k. Okay, and this one that's mean delta g over g. Okay, so in order to find the system accuracy in term error per output, so you can straight away uh, use that value. Okay, 0.175, that's mean 1.5 1.5 divide with 100. Okay, plus with 0.5%, that's mean, okay, I will write here 1.5 divide with 100, and then you plus with 0.5 divide with 100. Okay, now we got it, the system accuracy of your system is around 2%. Yeah, it's at 2%. Okay, right. In the root mean square, yeah, you can straight away use that formula lah. Okay, I don't want to go through into detail this one. Okay, precision and accuracy. The word precision and accuracy will give you the difference meaning. Okay, the difference meaning. Okay, don't accept that the precise is same with the accuracy. Right? How precise you are. Okay, precise that means how close you with each other. Okay. Accuracy that means how close you are with the target. That is the accurate, right? So this one will show you the precise. That means this is what is it? Aizat close with one. One close with the Yan. Okay, this one close each other. This close. When you got the data, you can describe, or your data is precise, but is not accurate. The accurate will be at this one. Okay, it's not accurate. Okay, that is the concept lah. So bear in your mind, precise is not same for like accuracy. Linearity, yes, this is what you have done in your experiment. Okay, you got this data. Yep, you got this data, 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 right? So then you will do best fit line, right? So that you can get the equation that we represent if you give the input and then you will get the output. Okay, right? So you will do best fit lah, fit line. And repeatability, okay, is when you develop instrumentation system, that means it has the transistor in and also you have the signal conditioning. When you try to get the data for today and then for tomorrow at the same condition, you should get it the same value. Okay, so if you get the same value from yesterday and today, that means your system will give you a good repeatability, right? It will produce the same data. So if your system not give the good repeatability, that's mean in terms of data from today and tomorrow. Okay, so that's mean you need to do some calibration. Okay, so like for example, right now when we go to the mall, right, and and sometimes the uh, temperature gun, right? So and then when we check, right? Oh, 37.3. Wow, it's hot. I cannot enter into the mall, right? That one is because the calibration. Calibration, that means the equation that they apply in order to show that the temperature value maybe is uh, wrong, right? So for example, okay, to get the temperature, and then this is the value that we read, okay, and then it plus with the uh, 2 degree, okay, we plus with 2 degree. So maybe this value they read from the ambient air and so on, so this value will be is changed. Okay, so that's mean you need to do the some calibration so that you can get the 2 degree. Okay, so how to do the calibration? So you need to have a standard device that you can compare on. Okay, for example, you have the temperature gun, right? Okay, how to draw the temperature gun? Okay, right, this one, right? Temperature gun. Okay, so you need to do the calibration. That means you need to shoot at what we call it. This one is the black body. Okay, black body, right? So it will give you the constant temperature. For example, 37. Okay, 37. So your temperature gun, it should read 37 degree. Okay, if that time your temperature gun read around 35 degree, that means your equation need to plus the offset is 2 degree. Okay, that is the purpose when you do the calibration. Okay, but this one is the standard device or standard material. For example, it's a very simple thing. The thermometer is a very accurate to measure the temperature. All right, so if you put your thermometer inside the hot water and so on, and then you will get the same value. Okay, for example, uh, 80 degree, and then you can put your instrumentation device in at the same hot water, you should get 80 degree also. All right, if you don't get it, that means you need to change the offset value. Okay, so maybe you can change it internally, or you can change later when you get your data, you change data, you change the offset. Okay, that is purpose of the calibration. Okay, we are done for this topic. Any question you going to ask? Any question? Ada apa-apa soalan tak? Okay. Any question, guys? No? No, guys? Okay. Can we take a break for 5 minutes? Okay. So you see you again at 11 2 minutes. 11 12 2 minutes. Okay. All right. Guys, I just want to ask, so whether anybody, every one of you are taking the mechatronic subject for this semester? Everyone? Are you taking the mechatronic subject? Mechatronic.
No,
No.
doctor.
No? Oh, Yan, you're not taking yet the mechatronic subject?
No.
Uh, Rizwan? No?
No, no, not yet.
Not yet? Oh, okay, okay. Aizat? Aizat Hamdan? No?
Belum. Tak ambil.
Okay. I thought that everybody taking the mechatronic. Is it in your uh, curriculum, Aizat? Awak SK apa? MM?
Bahan material.
Oh, material. So dalam uh, apa program awak ada subjek mechatronic tak?
Saya
Tak
pun
ada doktor.
Oh, tak ada.
Still
Oh,
like
Agak
okay, I
lagi.
see.
your year.
I see. It's okay. Because this semester I'm also teaching the mechatronic subject. Okay. If uh, uh, anyone who are taking the mechatronic subject, if you got any problem in terms of the project, you can ask me. Okay, I'm willing to guide you. Alright. Okay, Lazada. iPhone. Wow, 5,000 I tak mampu lah. Hanya orang kayangan je kan. Now we use the word kayangan, right? Alright. Okay, next topic is about dynamic characteristic. Okay, we are in the topic performance characteristic. So three type is operational, static dan error and accuracy dan dynamic. Okay, now we look into the dynamic characteristic. Dynamics, of course, some parameter that will change over the time. Okay, this is the dynamic characteristic. Okay. Uh, Static transfer function. Okay. When we talk about the system time response, right? Okay, that's mean when your input you give this one, so what will be uh, uh, what will be happen on your output, right, in terms of the time response. So you already learn this one in the control engineering. Okay, alright, some of you lah. Alright. Static, that's mean when you give the inputs. Okay, I just draw this one. You give the input. Okay, this is your input, this is your output, and inside this one is your transfer function. Okay, transfer function. When you give the input, uh, so you will straight away get the output. That means your input is constant. Okay, for example, the mechanical switch. Mechanical switch is like when you want to switch on the light, right? All right, at your home, you just click, tick, okay, and then you straight away get the output. That means the input is constant, right? That means is if it only give you the constant value, right? It doesn't affected over the time. Okay, that is static. Dynamic is it will affected over the time. When the input change, the output also will be changed. Okay, so for the dynamic, the graph will be like this one. Okay, and then your output also you will get the same behavior lah. Okay, like this one. Okay, so you will got the same output from the same input. Okay, and then of course in order to get the relationship between input and output, so we come out with the differential equation. All right, from the system itself we can come out with the differential equation, and then we can determine the order, right? So the order of the system, so whether it's second order, third order, or zero order, and so on. Okay, all right. This one I think you have learned in the control engineering. For example, we got the mechanical system here. So where is the xi is the input and x naught is the output. So when you give the force, right, from the left to the right, from here, then you found that the spring we give you the force back, right? This is the Ff, and then another point it will give you this force. That means force from the spring. Okay. Same thing with the damper. Yep, it will give you this one. So that's why you got it the direction of the force like this one. Okay. and then the relationship between the mass and the acceleration. So we get it from the Newton's second law, and then we will get it this kind of equation. This means this is the input, SI the input, and S naught is the output. Okay, so this one we call it the differential equation. Right. From the differential equation, we can determine the numbers of order. Alright. So whether it's zero order, first order, and second order. Okay. This one you have learned in the control system. Okay. But most of the system is more on the mechanical representation. So in this case, we want to look in terms of the transducer. We can specify it in term of zero order, second order, and so on. Okay. For the zero order, it's like the potential meter. Okay. So that means it's a static transfer function. It doesn't affected by the time. Okay. So this is the for example, right? So let's say the input we want to set is a degree. Okay, which is the angle. Okay, and then the output it will give you in term of resistor. Okay, right. When you measure no, let's say we put it is the millivolt. Okay, right, voltage. Alright, so inside this one is your ODE, differential equation DE. Okay, right. So when you give the angle, you try to turn the knob at the 10 degree. So it will give you the straight away is, for example, 2 millivolt. Right. And then when the time, that's mean the value is doesn't change over the time lah. Okay. First order. Yep. The first order, the equation here is uh, you got it this one y and u. Y is the output, u as the input. Then we can get the very general equation for the first order is k divided 1 plus d d. Okay, your d that's mean is uh, transfer function of the d equal to d over dt lah. Okay, so on the first order, there are two parameter normally. Okay, affected is k is the gain, and also the t, which is the time constant. T is time constant. Okay, this is be careful with this word. This word is time. Okay, it's not the value of voltage and so on. Time constant, where you can get it at the 60% of the final output. Okay. This is the word. It's a time for 60% of the final output. Okay. So let's look what of the type of transducer that behavior that behave like first order. Okay. Alright. For example, the transducer is called thermocouple. Okay, thermocouple. We detect the temperature, and then uh, it will produce the voltage. So we can draw the block diagram here. It detect the temperature, and then it will produce the voltage. Okay, okay. That means I can write the time response like this one. Okay, so over t, the input is degree, the output is millivolt. Okay, you need to be able to draw like this. Okay, you need to be able to draw to understand the concept. Okay, then your thermocouple to detect the temperature, your temperature is not start from the zero, right? Because the ambient temperature right now is almost 25 degree, or maybe 20 degree if you turn on your air conditioner, right? So this, it will not start from the zero, and then the temperature will increase. Okay, will increase, into the certain temperature that you set, and the same time response will be happen on your output. Okay, that is the first order system. Okay. However, at the output, you will got it is you will have the time constant. Where is time constant is 63% of the final output. Okay. For example, let's say we set it the maximum we want to set is 1 degree. All right. So and then millivolt based on the transfer function is it give you 1 millivolt. Okay, and then the final output is 0.63, right? Then you will get it your time constant here P. Okay, so far clear tak? Clear? Okay tak? The concept, guys, clear?
Clear, doctor.
Okay, thank you. Time's up. Good. All right, thank you. Okay. All right. First order time response is show to this graph. Before that, who's not yet taking the control engineering? Siapa yang tak ambil lagi control engineering? Can you raise your hand? No. Okay. Everybody has taken the control engineering. Good. All right. For example, the first order. Okay, the first order you set it is you want one. Okay, the value one, and then you will got it this kind of graph. This kind of graph. This is the first order equation behavior. Okay. Now you will see that yep, it will have the time constant here. This is the time constant where is the value is 63% times with 1, you got it 0.63. Okay, and then after that you will got it another time here. Okay, t1 and then another time. Okay, another time here I put it is t lah. Okay, the time. Okay, all right, t1 and t2 and so on. When you want to start measure your data, sorry, when you want to start to get your data, where do you think which point that you can start to measure your which time that you can start to what you call it to collect your data? Can you tell me which time? Is it at this time? Yep, you can get your data. Oh, this is my data. Okay, is it this time you can get your data? Oh, this is my data. Or this time, right? Or this time, or this time. Which one? 1, 2, 3, 4, 5. At which point? What do you think? To get your data to be accurate. Okay. Uh, you will conduct an experiment, and then you will get it. Oh, okay. At time constant at the 1 second, okay, you will get the data. Oh, this is my data. Maybe 2 seconds. Oh, this is my data. Which point that you think will be an accurate data? Agak-agak yang mana? Point mana? 1, 2, 3, 4, 5. Which one? Anybody can answer that? 1, 2, 3, 4, 5. By how? Which point that you think? Because this question has been asked last semester. Which point that we represent the accurate data? By Hong, Jackie Tang. Wow, Jackie Chan, Jackie Tang. You want to answer that?
0.5.
Yeah. Who's that? Kusai. Yeah, Kusai. Kusai, nice to meet you. You are from where?
From Syria.
Syria.
Yeah.
Oh, last time your control engineering, you got A, right?
Yeah, I was taking it with you. control.
Oh, okay, okay. You are, I think, you are a good student because your when I marking your answer, I can see that. Okay, good. Right. Good answer from Kusai. So I call you Kusai, right?
Yes.
Yeah, yeah. Okay, Kusai. So the point five, we give you the accurate value, right? What is mean the accurate value? That's mean the value that is close to the input, right? This one, if we learn the content engineering, this one we mean the steady state error lah. Okay, all right. This is the answer. Thank you, Ustaz. All right. In control engineering, most likely our input is starting from the zero. Okay, from the zero. However, in the instrumentation, right? Because the instrumentation is try to measure quantity, right? Most likely our quantity is not starts it's not starting from the zero, right? Okay, for example, your temperature, ambient temperature, maybe it start from 20 degree, okay, right? And then it can go up to 40 degree, for example, okay. Other example is like heater, right? Heater. So this one has been used in cool country like UK and so on, right? I believe Kusai, your home also have some heater, right? During the winter season, right? Is it?
Yes. Yes.
Yeah, yeah. I just want to share my experience when I at UK about 2 years, right? 2 years and a half there. So, yep, I just rent an apartment, right? That one. When you live in cool country like UK and so on, you will have heater, right? They don't have the air conditioner actually. They don't have it. They only have the heater. And then uh, most of the Malaysian people, right, who live there, so they try to save the cost, right? To save the cost. That's mean they will open the heater when they want to take uh, that's mean they want to take the shower, right? For the bus, right? Only that time. That's why when you stay at UK, you will find that most of the people we take the bus is only one per day. Some of them we take the bus maybe one per week. Okay. My experience when I go to very what kampung lah. That's mean very far away from the town. When you ride the bus, right, you can smell that. Wow, from the especially from the eldest person, right? Eldest person, because yeah, that's is the reality. Okay. Because the the price to the bill, right, to turn on the heater, right, is very expensive. I don't know, maybe Usai, is it true? The price or the electrical bill, right, for the heater is quite expensive, right?
Yes. Usually turn it off.
Uh, yeah. Do you turn the heater for for 8 hour or more than 8 hour during your the winter? No, right? I don't think so.
We usually have the fire one, not the electric.
Yes, yes, yes. If you have the fire one, that one is okay lah. But in UK, you need to use the electrical heater, or maybe you can use the gas heater. Yeah, that one. But yeah, some of you just heard that. Wow, UK. Oh, doctor has been to UK. Wow, it's good, good. Yeah, you need to go there. Go there for the 2 weeks or more. So I will give you some guarantee that you want to come back to Malaysia. Right? Because yeah, it's It's only like yeah, good, UK or sejuk is cool, and then when you go there around 2 weeks, and then you feel that you cannot handle it anymore. It's too cool. I want to go back. I want to go back. Right? This is what happened lah. Okay. During my study lah at UK, and also during the hot season, right? Because they don't have the air conditioner. They don't have it. Then you need to use the fan, right? So can you feel the that time? Wow, it's a very hot, and also their air environment is a dry environment, right? It's not our country. Our country is humid. Like our country, yeah, you just stay at home. You can sit on the aircon at any time, right? Because your parent will pay it for you, right? Okay. All right. Where am I? Okay, I'm at home. All right. For instrumentation system, for the first order, it's not start from 0 degree. For example, the temperature lah. It can be start from at one point. For example, 20 degree. Okay. So this is the equation that we describe the first order for the instrumentation system. Okay. All right. So let's look example 4.1 here. Okay. Alright. A sensor measured temperature linearly with a transfer function of 33 millivolt per degree and has a 1.5 second time constant. Okay, find the output 0.75 after input change from 20 to 41. Okay, let's add this one and then rotate. Okay, done. Okay, so this is the information that you got it here. You heard the linear equation here. Okay, so we can put it temperature. So it start from 20, and then the end is 41 degree. Put it at 41. Okay, and then it start from 20. And then this is the temperature over time, because it's the dynamic response. Okay, and then the output, you should get the same dynamic, same behavior with the input lah. Okay, because this one, the output will be most of the same with the input, and then the output you got it millivolt, and then your output which have the time constant 1.5. Okay, and then it asks you what is the output for 0.75 second. What is the output? Okay, what is it? Right? Okay, yes, is the question is about find the output. Okay, what is this value? Okay, all right. So in order to do this is quite simple. You can get it here. So you can write the y t, okay, y initial plus minus y final minus y initial, you time with 1 minus t over time constant. Alright, so we can find the y initial first. Y initial, that's mean here, y initial, y final is in here. So you can get it y initial from the 20. Here you time with the transfer function. Okay, so 20 degree we time with 33 millivolt over degree. Now you got it is 660 degree millivolt. Then you can find the initial 40 degree time with 33 millivolt over degree. Now you got it is 1353 millivolt. Then you can use the equation we want to find at 0.75. So this one plus 1353 minus 600, 1E 0.75 divide with time constant 1.5.
Doktor,
Okay.
kenapa wifi dia ambil 40 degrees ni bukan 41 degrees?
Oh, sorry. Thank you. Okay. Berjagalah kerja saya ni. Okay, good. You still working, still focus on my lecture. Thank you. Okay, 41. Okay, then you got the answer, 1353. Then this one, the final one, you got it 932.7 millivolt. Okay, here. This is the final answer. Alright. Okay. Okay. Alright, guys, are you done? Sudah. Thumbs up, and if you are done, copy or Milo or Nescafe. Okay, Francisca. Wow, Francisca Pawi. Nama sedap. You are not from Perancis, right?
No, doctor.
Have you that's mean have you went to Paris? So what you call it? Eiffel Tower, Eiffel Tower. Sudah pergi sana belum?
Belum, doctor.
Ya, indah khabar dari rupa lah. So if you go there, you will see that wow, there are one common, one smell. If you just go out from the train, right? So you will smell that thing. That is the Eiffel Tower, right? Okay, and yep, this one. We got it. This value 982.7 millivolt, and then what is the temperature? So you can get it back. So X you time with this one, and then you can get the temperature here. Okay, and then the error lah, the error that you got the reading. That means you got the reading here. Okay, the final one should be 41, but you got the reading is 38.3. So this one will be the error lah. Okay, error is 12.7 degree. Okay. Okay. So another one is about second order response. Yep, we not cover this one in this subject lah, but it's good thing for your information. The example of the instrument that behave like second order system, right, is the accelerometer. Right, accelerometer, we have learned this one. We have not learned this one, but we can draw the mechanical um, system. Is like is you use the M and a spring, right? So when the mass move there and then move right, so this is the simplest system for the accelerometer lah. And then what it will behave like this one, right? Right, and then it will have some damping ratio and so on. Okay, and then you can adjust in this one the dam, right? Or and then the response also behave like undamp, underdamp, overdamp. Yep, we have learned into this one before. So the damping is depending on the K and the mass, and also sometimes you got it with the damper, right? Okay, so this one should have the damper here, right? So in the instrumentation, it just for your knowledge lah with the accelerometer. Okay. Right. Okay. This is the reading exercise. Okay, it's not the reading exercise, so I would like to give you the assignment. Okay, assignment. Okay, this is your first assignment for this subject. Okay, alright. So you just try to answer what is the importance of standard deviation in the data measurement. So I have discussed this one last week. And then what is the define the three type of performance characteristic. So we have learned today. Okay. And then number three, the process flow to know the performance characteristic. So what is the process to know the performance characteristic? Okay, process flow. And then the important to know the performance characteristic. Why we need to know the performance characteristic? Okay, what is it? Okay, so try to done this assignment. Okay, the time is I think the 1 week lah. So next week you can submit through the e-learning. I will open the link in the e-learning. Okay. Right. Uh, any question about this one? Any question? The assignment? Any question about this topic? No? Any question? No? Okay. Alright. Can I move to another topic? I'm not I know will be covers the whole topic for today, right? But because of the test one, it will be on upcoming week. So hopefully I have covered the all topic. Okay. Or you want to take a break for 5 minutes and then we can come again to go to the next topic. Nak take a break first or what? Boleh? Nak take a break? Macam mana?
Boleh, betul boleh.
Take 5.
Take 5. Okay. Pasca Fawi ya, she request to take 5. Take 5. 1, 2, 3, 4, 5. Yep, already take 5. Alright, I will see you again on 5 minutes later. Okay. All right, guys, done. 5 minutes, done.
Okay.
Okay. All right. Good. For the assignment, right? So, the question one and then the question two, I think you can answer that. The process of flow. Yep. So, what is the uh, process of flow? That's mean what you need to do to know the performance characteristic. Okay. So, performance characteristic. When talk about performance characteristic, that's mean there are three type, right? Three type. Okay. The first is the operational, and then what is it? Static, and then also the static for this one. I also forgot it, right? Where is it? Dynamic and static, and also dynamic. Okay, and then why we need to know the performance characteristic for implementation. So operational is quite important to know when you want to choose some sensor to do the some measurement and so on. And then static internal error is quite important to know, right? Of the instrumentation of the data you got it, right? After that, you need to know the accuracy. Okay, and then the dynamic is important when you are taking a data, right? Okay, that's one is quite important. Okay, all right. So without further ado, so let's move to the next chapter, which is the signal conditioning. Okay, so signal conditioning, this one come back to the instrumentation system. Now you got the transducer, and then you got it the signal conditioning. Okay, alright, so this is the transducer, and then this one is the signal conditioning. Okay, so that's mean transducer, maybe you detect degree, temperature, and then you with the output will be millivolt, and then this one you will amplify it. Or some of the transducer also detect degree, and it will produce the output in terms of resistance, and then you need to have the signal conditioning to convert in voltage. Okay, alright. So, it's not signal conditioning is not about the level change, right? Level change, that mean it can use to amplify from the small voltage to be a large voltage. It also can do the attenuation from the large voltage. It can become the small voltage, right? And for the conversion, it also can convert it into resistance to millivolt, for example, or maybe it can convert it into uh, uh, capacitor, okay, farad to millivolt, okay, and so on. Linearization, yes, when we can uh, construct, right? We can build our signal conditioning to make our data become linear, right, and so on. But it's quite difficult to do in terms of the hardware. So normally we use the software. You just use the best fit line to get the linear, right, linear equation. Filtering, signal conditioning also can use uh, as the high pass, as the filter to filter out the high pass, low pass, and band pass filter. So this one I just want to share it to you. So this semester I teaching the mechatronic subject, so I need to develop some module in hardware and so on. I'm also write some coding. And it's not coding, the module. Yep. Ignore the cartoon one. It's because my my daughter. Right. Yep. Yeah. I I developed this module and so on. Right. So I okay. Uh, just want to share the experience. So I don't know how the we call it a YouTuber, right? YouTuber create their video, right? Every week and so on. For me, it's quite difficult because, yeah. we need to have some script and so on. And sometimes we need to have the good mic or the good environment, right? Because of the noise, right? When I try to what we call it, to eliminate the noise, okay? For example, this is my voice, right? This is the noise. Right, this is the noise. Okay, so yeah, it is quite difficult to what we call it, to cancel this noise. Okay, the noise mean when you have the fan, right? And yeah, you need to be in a special room. That's why at that time they put like span there on the wall and so on, right? So for those who like go to what we call it, jamming, right? They know about that one. So it should be in a special room. Okay. Right. Okay. Signal conditioning also can be used as the filter to filter out the unwanted noise. Okay. So this is a summary. It also can be used the comparator. We will look in on the next subject and so on. Okay. All right. Before we go into detail about signal conditioning, so there are one what we call it, one concept, right? That will be useful for you if you play around with some electronic circuit. Okay. Uh, uh, that concept is called the Thevenin equivalent. So Thevenin equivalent, that means from the guys named Thevenins, right? So he had developed some theorem to simplify any linear circuit. All right, no matter how complex is it, you can simplify it. Uh, for example, let's say this one is the complex circuit. Okay, complex circuit. That means it will have one supply voltage and three resistor. Okay, by using the Thevenin theorem, you can convert it. You just need a one supply voltage and only one resistor. That means you can save cost about in term of resistor lah. Okay, so this is the complex circuit lah. For the electrical student, right? They learn this one in their first year lah. Like us, we learn about static. So like them, they learn about theory circuit theory. Yep, circuit theory. So how can they simplify this one to be like a simple one? Okay, so we want to look a little bit about Thevenin theorem. So what is the Thevenin theorem? You only need a voltage Thevenin's VTH and also resistance Thevenin. So how to get the voltage Thevenin? So it's simple. So what you need to do is you need to find the output voltage, right, at the terminal AB here. Okay, AB here. So this one, that means is VAB. So your V voltage Thevenin is equal to this one, the voltage Thevenin equal to VAB equal to R2 divide with R1 plus R2 you time with Pin. Okay. So this is the VTH, alright, voltage Thevenin. So R2 divide with R1 with plus R2 is the voltage divider concept. I hopefully you know about it. And how to get the resistance Thevenin? So you just shorted the supply voltage, short here. Then you will see that the circuit will be like this one. Okay, this is point A and B, and then the resistor is R3, R2, and R1. And this is you going to find the RTH. So how to find the RTH? RTH, you will see that the resistor R1 is parallel with R2, and then you will plus with R3. After it parallel, it becomes series, right? After serial, it becomes series. Okay, and then that's why you will plus with R3. Then you need to find first the R1 parallel with R2. So how to find this one? Let's say I have the Rx, okay, is a symbol, 1 over R1 plus 1 over R2. Then you can find the Rx is equal to R2 times R1 divided by R1 plus R2. Okay, so I just make it simple this one. So Rx, I go there, okay, go up, and this one R1 times this one times this one, and then both will go down. Okay, that's why I got it this one. Okay, and then the final one you will get it is RTH equal to Rx plus with RT. Okay, all right. That means you when you got it this value RTH, for example, you calculate you got it is 100 ohm. Okay, and VTH, for example, you got it you calculate it you got it about 10 volt. That means the equivalent circuit by using the theorem Thevenin, so you just need to buy right only the 10 volt supply and also 100 ohm resistance. It will give you the same output with this complex circuit. Okay, that is the purpose of Thevenin theorem. Okay, alright. So far, do you have any question regarding this theorem? Ada apa-apa soalan? Tak ada?
Tak ada.
No.
Okay, tak. Okay, alright. A few more slides, right? And then we will end our class. Few more slides. Okay, good. Right. So next one, rotate this space clock. Right? Oh, how to do that? Oh, lemah. Rotate this place counterclockwise. Okay. Rotate this space clockwise. Oh, okay. Okay. After that, let's look about concept of loading. Okay, concept of loading. What it mean? Okay, I try to explain that here. Okay. Uh, for example, we buy the temperature sensor. Okay, to give you the idea. Right? For the temperature sensor, it will convert it into voltage, right? For example, the millivolt into voltage. And then you connect it into the loading. For example, you buy a temperature sensor to turn on the motor, for example. Okay. Then your temperature is detect about 20 degree, right? And then the output is 1 millivolt. So not enough to turn on the motor. It need about 40 degree to turn on the motor, 10 millivolt. Okay, to turn on the motor. Okay, motor ada ke 10 millivolt? Okay lah example. Okay, alright. Okay, so what is mean the loading is mean this motor also have their resistance, which mean RL, loading. Okay, another example is like when you want to check the output from this transducer, you use the multimeter. So that multimeter also will have the resistance. That resistance we call it is the loading resistance. Okay, that's it. Alright, and then inside the transducer, it also have the what we call it internal resistance. Okay, that means, for example, 20 degree and then we convert to transfer function, then we got it is VT, voltage transducer. Okay, because it will produce some voltage here, we got a VT. And then that VT, before it go through to the loading, it will have the internal resistance. This one, we call it is RX. Surya Baja Hitam, RX. No. Okay, RX. Okay, this what we call it is internal resistance for the transducer, and then you will also have the loading RL. Okay, that is the concept. Okay, and I can label it this one to make sure it's same with this slide. So this one I put it is BL, and this one I put it is BX. Okay, then the equation for BL is Vy, sorry, Vy. So I choose this output like Vy. So this one Vy, Vx. Then this one will be equal to Vy equal to uh, Vt minus Vx. Then you will got it is the Vy equal to Vt times with 1 Rx over Rx plus Rx. Okay. Uh, so how to get the equation, I don't want to discuss in the detail. Okay. Alright. The concept of loading, that's mean this is the loading. Okay, this is the loading. This is the concept. Right. So when you have something yeah, like for example the multimeter, you measure transducer. So multimeter will have the loading. Okay, or maybe if you want your transducer to turn on the motor and so on, so this one will be the loading. Okay, all right. So this is the last example. So let's look before we take we end our class. Okay, example 5.1. An amplifier output has a voltage that is 10 times the voltage on its input terminal. It has the input impedance of 10 kilo ohm. Okay, this is the the amplifier, right? The symbol is this one, triangle, and it have the input impedance. That means the RL, the load. Okay, equal to 10 kilo ohm. Right. Okay. A sensor output has a transfer function 20 millivolt per degree. Then the sensor has internal resistance 5 kilo ohm. Okay, here 5 kilo ohm. If the temperature is 50 degree, 50 degree. Now the temperature is 50 degree. Right. Find the amplifier output when the internal and loading is ignored. So find the V out. Okay, that is our purpose for this question. Okay, there are two conditions when the internal and external, right? Internal and loading, okay, is ignored, and then the second one is included. Okay, for the first condition, when the internal and loading is ignored, that means there are no resistance there. Okay, there is no resistance there. All right, and also with the loading, there is no resistance there. Okay, what you we got it is like this one. Okay, 55 degree. Okay, and then you need to find the V out. Okay, so if you can see that the V out equal to 10 times with V in, because the amplifier is amplified with the gain 10. Okay, now how to find the V in? The V in equal to Vs. All right, in this case, because there is no resistance, so we can straight away get V in equal to Vs here, V in here. So what is the value of Vs? Is 55 degree you time with 20 millivolt per degree. Now you got it as 1 volt. Okay, so in this case your V out equal to 10 times 1 volt equal to 10 volt. Okay,
50 Celsius, right, sir?
55, right? 50. Oh, okay. Thank you, girls. Ini suara girls ni. Biasanya girls kurang aktif. Right. Thank you. 50 degree. Okay. Alright. Now you can get it V out equal to 10 volt. Alright, that is the concept. This is the V out. Okay, this is the V out 10 volt. Okay, the next is we want to look if the internal and loading is included. Alright, included here. So the circuit will be like this, right? It have the resistance and it also have the loading. Okay. Now the V out here is still equal to 10 times with V in. Okay. So how to find the V in? How to find the V in? V in is equal to, yep, this one only the voltage divider. Alright. So 10 over 10k over 5k plus 10k. Now you need to time with the Vs. Okay. So in this case, you got it is what you call it Vs. Vs is this one 10k divided by 15k. We time with Vs equal to Vs that we got it before is 1 volt. So 1 volt. Then we got it is 0.667 volt, I think. Okay. Alright. Then this one, your V out is 10, you time with 0.667, then you will got it 6.67 volt. Okay. Alright. That is the concept of loading lah. Okay. In this case, our loading is the signal conditioning. Okay, guys. Last but not least. Last but not least. Do you have any question? When you have the loading, that means your output voltage will be dropped lah. Okay, that's it lah. Any question regarding our lectures today? No? Guys, no? Any lecturer? Any lecture? Any question?
No questions.
No question. Thank you very much, Rizwan. So I think we will stop at this page, right? We continue with another lectures. Oh, good. Clap your hand, right? Good. Okay. I think if you have any question, you can WhatsApp me directly. And see you again on next week. And don't forget your assignment, right? I will click the link for you to submit, right? Okay. Thank you, guys. That's it for today.
Thank you, Doctor.
Thank you, Doctor.
Have a nice day.
Thank you,
Bye.
Doctor.
Welcome. Assalamualaikum and good afternoon.